Good day, everyone. Welcome to our midterm reviewer for differential equations. Before we start, let's have a short recap of the formulas before proceeding to variable separable and homogeneous differential equations. Then we proceed to exact and linear differential equations, followed by integration by parts and more assorted examples. So feel free to take a screenshot of these slides if you will practice for our exam. So we have the basic differentiation theorems, the chain rule variables, laws of exponents, the laws of logarithms, the derivatives of exponential functions, and the derivatives of logarithmic functions. So the ones on this slide will be the most commonly used ones since we'll be dealing a lot with ln and e. So you'll see those later. So make sure to familiarize yourself with the laws of exponents and the laws of logarithms. Next, we have trigonometric functions. You don't really need these that much, but do take note, you'll be encountering sine and cosine a lot. So sine and cosine are always paired. Getting the derivative of sine gives you positive cosine, and getting the derivative of cosine gives you negative sine. So remember, sine positive, cosine negative for differential calculus. So for integral calculus, we will be using the ones on these slides a lot as well. So the difference between integral calculus and differential calculus is that when you apply the power rule, you multiply by n first and then subtract 1 from the exponent. In integral calculus, you add 1 to the exponent and then divide all of that by the exponent plus 1 plus c. Next, you have the change of variable or use substitution. You're going to use this when you have multiple terms raised to an exponent or inside a radical or inside any other function. The chain rule works similarly to the power rule. Next, we have the formulas for exponential and logarithmic functions. So as I mentioned earlier, we will be encountering a lot of E and U here. So in particular, there's a lot of this used for these problems because we usually encounter dx over x, especially in the variable separable method. Lastly, for the integration by parts, we usually use these with exact and linear. So it follows the formula uv minus the integral of v du. And then the priority is by Liate. So this is an acronym for choosing the U, which should be easy to differentiate. Logarithmic and inverse, followed by algebraic, followed by trigonometric and exponential. So you follow this order when choosing your U. The V is simply going to be the other variable and the dx or the dv or whatever it is. So this V will be easy to integrate. As for these formulas, you won't be using these much. Probably the only ones you'll be using are cosine and sine. So cosine, remember in integral calculus, cosine is the one that gives the positive and sine becomes the negative. So recall earlier, um, derivative of sine is positive cosine x and derivative of cosine is negative sine x. Here is different. Derivative of cosine gives you the positive x. Sorry, integral of cosine gives you positive x, positive sine x, and the derivative of sine gives you negative cosine x. So next up, we have the partial fraction method. So we have one example of this later. But basically, what you need to know for now is we can factor the denominator and split it into two fractions. Then we basically solve for what the numerator will be for each fraction. So we'll elaborate more on this later. So that's the end of our short recap for the formulas. Now we can proceed to separable and homogeneous differential equations. So first of all, we need to know that the coverage of this test will focus on first order, first degree differential equations. So these are equations involving a dependent variable, its independent variable, and its first derivative, with the highest power of the derivative being 1. It's generally expressed as dy over dx is equal to the function in terms of x and y, or as m, it's basically the function with dx plus n, which is the function with dy equals 0. These equations can be solved using various methods, and the first one we have is variable separable method. So you can identify it from the name. Variable can be separated. So if you can group all the if you can group all the dy and y terms on one side while placing all the dx and x terms on the other side, it is variable separable. So for our given, dx over dy is equal to 6y squared x. You can move this to the right side of the equation, and then you move the x onto the left side. So you're going to notice that dx over x has all the x terms, and 6y squared dy has all the y terms. So this is our variable separable. Example. For dy over dx is equal to x cubed plus 2x, we move dx to the other side. So now dy is on an opposite side of the dx, and all of the x's and y's are separate. Now we can integrate both sides. So what you're seeing here is the power rule for integration. X raised to 3 becomes x raised to 3 plus 1 divided by 3 plus 1. So we have x raised to 4 over 4 plus the 2x is going to become 2x squared over 2, which is basically 2x. And then don't forget the plus c. So you can put the plus c on any side, but for this video, I'll be putting them on the right. So next, you can now distribute the integral for each term. You will know when your differential equation is solved when there is no more dx and no more dy. So in this case, it is already solved. Next, we have dy over dx is equal to 3 over x. So simply move them to opposite sides. So dy is equal to 3 dx over x. You can pull 3 out of the integral sign, so you have dx over x. So the integral of dx over x is going to be ln x. So in some textbooks, they use parentheses, while the others use absolute value. For the purpose of this video, I'm going to assume the form where it's in parentheses. So this is a final answer already. Next, we have dy over dx is equal to 4 cosine 6x. So when you move dx to the other side, you're going to have this inside the integral. So note, first of all, cosine is going to result in positive sign for integration. So we have sine 6x. And recall that chain rule applies to what's inside. So inside the function cosine, we have 6x. So if you do it the long way with u substitution, you're going to end up with 1 over 6 sine u. Or rather 1 over 6 cosine u, or something like that. So a shortcut, if you have something like this, you simply write sine of this divided by the number. So sine 6x over 6. So that's the shortcut. Simplify it, it becomes 2/3 sine 6x plus c, and then this is the final answer. Now you may have noticed that we all equated it to y in this slide. So in expressing our final answer for variable separable, we usually express it explicitly as y is equal to fx plus c. So only leave it in implicit form if solving for y is messy or impossible. So for example, if it's inside um, L and Y, or if the directions specify otherwise. So next, let's have a harder example. We have dy over dx is equal to 4 over x squared minus 1. So first, you want to move dx here, and then take the integral of both sides. So now, for partial fraction decomposition, this is what I mentioned earlier. You can use this when you can't use u substitution. So if you try u substitution here, you're going to get u is equal to x squared minus 1, and then du is equal to 2x dx. So you can't really use it because of the x dx. So you proceed with partial fraction decomposition. So x squared minus 1 factors into 1 plus 1 and x minus 1. So you know the denominators, but you don't know the numerators. But you do know that when you add this, it should become this number. So in doing partial fraction decomposition, you just cross multiply. Multiply this, multiply that, and then get rid of this. So a times x minus 1 plus b times x plus 1 is equal to 4. So you want to find a 0a and a 0b. So you can just be left with 2b and 2a, right? So in order to do that, you just set x to make one of them 0. So to make x minus 1 0, you have to set it as 1. And then this will become 1. So 0a plus 2b is going to become 4. And b is going to equal positive 2. Next, to eliminate b, you need negative 1 and negative 1 here. So this becomes 0. And then you have negative 2a is equal to 4. So a is equal to negative 2. So basically, we rewrote this part. We made it go through partial fraction decomposition. And now it is this. So this is much easier to integrate. So what you can do is distribute the dx and then perform integration. So you're going to be left with, so the first one is going to be negative 2 integral of dx over x plus 1. And the other one is simply going to be that, but positive. So again, when you have this dx over x, you can check the bottom if you can use the shortcut. So earlier, we said dx over x is equal to ln x. So when you have a linear denominator, like x minus 1, you don't need to do the long u substitution anymore. You can just, wait, no. To be specific, you have a linear denominator with no coefficient. So if, for example, you have dx over 2x minus 1, don't do the shortcut. You have to do it the right way with u substitution. But if it's just like this, you just put this inside the ln sign. So our answer will become y is equal to negative 2 ln x plus 1 plus 2 ln x minus 1 plus c. So next we have xy dx plus x squared plus y squared dy equals 0. So if you have something like this, first try if it is variable separable. So as you can see, you have xy here and x squared plus y squared for dy. So this will be something we'll use a lot in answering these kinds of questions. M represents the terms with the dx, and n represents the terms with the dy. So you can replace this with other variables, but most commonly you have x and y. So as you noticed, we can't separate the x and y easily because of this and this. So next, we check if they are homogeneous. So there are two ways to do it. The first being by visual inspection and the lambda test for homogeneity. So we're going to do the visual inspection one, and the lambda test will be done later in a next example, near the end of the video. So here we have exponent of 2 and then exponent of 2. So what about xy? Xy has 1 for x and y has 1. So if you do 1 plus 1 is equal to 2. So with all the terms having an equal exponent, we could say that they are homogeneous. So for the lambda test, it's about replacing x and y with lambda x and lambda y, and then factoring out the lambda. So basically, you're just counting the exponents and seeing if all the terms have them. So next, we choose a simpler m or n. So we can see that this one is simpler. It's easier to compute with. So here we check which of the terms is simpler because basically we want to replace the x's and the y's here with something that lets them match the dx and the dy. So let's elaborate on that soon. Um, we substitute x is equal to vy if the dx term is simpler because this will make our computation shorter. So we are looking for x and a dx. So where is it easier to substitute something that is two terms? Is it here or is it here? So it's easier here because this one, substituting it here will make it need for method, and that will get long. So essentially, the gist of this is you set x as vy and then dx equals vy with the product rule applied. So here's what I'm talking about. We're going to substitute dx with this and the x with this. So let me write it down. X becomes vy. So look for all of the x's. And then dx becomes vdy plus y dv. So again, this is done so that we can make the homogeneous differential equation into a variable separable. So simplify. So after multiplying this, you get vy squared, and then you distribute it to the terms. Similarly, when you get vy in parentheses squared, the v gets a square and the y gets a square. So don't forget that. So when you arrive at this one, you need to check the dy and the dv's. So first, let's start with the dv because I like to do it alphabetically. The dv, there's only one dv, so you keep this isolated on one side. Next, we have the dy's. So you notice they have dy, dy, and dy. You can also notice they have y squared. They all have y squared. On the other hand, vy cubed is present in dv. So keep that in mind. Factor them towards variable separable. So we bring out the y cubed and we bring out the y squared. And then inside the parentheses, we have the v's. Next, move this to the other side. So you have is equal to negative y cubed v dv. And then when you have this dy on this side, you have to move this to the other side. And then this one, 2v squared plus 1, will go here in the denominator. So an important thing, there's no need to bring the fractions. There's no need to bring, there's no need to bring the negative signs with you. And sometimes you don't even have to need to bring the fractions because this should be present on this side. So now you want to take the integral of both sides, but you notice that this denominator is a bit complicated. So you can use u substitution for that. Set this denominator as u, and then you can turn this dv into du. So first, let's integrate with u substitution. So let u equals the denominator, and getting the derivative of that, we have 4v. So move the dv to the side, we have v dv, and then move the 4 to the other side. So we get du over 4. So again, you can substitute the denominator to be u, and the numerator becomes du over 4. And then we put it in the integral sign. We grab the 1/4 and bring it out. So now we are left with dy over y becoming ln y, and du over u becoming ln u. So ln u is going to be ln of 2v squared plus 1, since the u substitution is now over. And then don't forget the plus c. If you are going to express your value in terms of c, then simply move this to the other side. So you have ln y plus 1/4 ln parentheses 2v squared plus 1. This can already be a final answer. If you prefer your final answers to be not in ln, what you could do is multiply them. So adding logarithms is equivalent to multiplying the numbers inside the logarithm. So you get y times 2v squared plus 1 raised to the power of negative 4. So maybe wondering, where did this negative 4 come from? It came from here. So multiplication, just like addition, becomes higher in a sense when you put it inside an integral. Um, Higher multiplication becomes exponentiation, and higher division becomes taking the nth root of something. So this one inside 2v squared plus 1 can be rewritten as 2v squared plus 1 raised to negative 4, or the fourth root of 2v squared plus 1. So this one is much more easier to work with, so we use this one. Now, the c on the other side, you can replace it with ln c, because um, constant, taking the logarithm of a constant will still result in a constant. So that's why you can just keep c there. So taking ln out of both sides of the equation, you get y is equal, sorry, y times 2v squared plus 1 all raised to negative 4 is equal to c. Lastly, return to your original variables. Remember that x was originally, sorry, um, rather vy was originally x. So that's why um, in solving for v, you move y to the denominator. So you get v is equal to x over y. Substitute it here, and you should get this final answer. So you can simplify it further, but to my knowledge, this is already acceptable. So, according to textbooks and even online sources, for homogeneous differential equations, you want the final answer to be expressed in equals c. So that makes it clear what the final answer is like. So now we proceed to exact and linear differential equations. Just like separable and homogeneous DEs, these ones are very much interconnected. So for the first example under exact differential equations, let's assume we have tested variable separable and homogeneous, and it still didn't work. So now we proceed to the test for exactness. So we still follow the same general model, and this time we are looking for m sub y and n sub x. So it's basically we're getting the derivative, the partial derivative with respect to the other variable. So if this is dx, then you're looking for the y. If this is dy, you're looking for the x. So getting the partial derivative of both of them, we remove the things that we don't need. So here in partial derivative, with respect to y, we're only interested in y, so this becomes 1. And then the rest of it is treated like a constant. So this one, negative x squared is going to become negative 2x. So if these are the same, then we can say that it is exact. Next, we integrate for f of x and y. So integrate all of this, and this will be in here. So integrating that will be this plus a constant, or in this case, a variable of integration that represents a function or a constant. And then we have fxy on the other side. So we can get this fxy by integrating the simpler one that we have chosen. So let's integrate it now. Integrating with respect to um, y, we have 4y cubed. The cube becomes 4. And then we divide by 4. So we're left with y to the fourth minus x squared. Since x squared doesn't have any y's in it, we simply copy it and then give it its own. So we have the simpler. So we're done with that, plus the variable of integration. So now if you get the partial derivative of both sides, the ky will become k prime y, and then the hx will become h prime x. So let's focus on what we are doing. This one, we're already done here. Ignore the integral sign. This one is supposed to be the integral of n xy dy. So now the hx earlier is now h prime of x, and we are to get the partial derivative of this one. Also, getting the partial derivative of the whole function only with respect to x makes it so that this is our mxy. So mxy is the only part concerned with x. That's why we have it here. So now, let's see. I'm getting the partial derivative of y to the fourth minus x squared y with respect to x. We don't need this part anymore. We only need negative x squared y. So now you can substitute this here. This is now going to be negative y times 2x or negative 2xy. So you can see that there are two 2xy's on both sides of the equation. Simply cancel them. And then isolate h prime of x. Once h prime of x is isolated, take the integral of both sides with respect to the variable inside. So now that we have reached here, we can now take the value of h of x without the prime. So the integral of 1 dx is going to become x, and then we add plus c. Lastly, we get this and substitute it in here. So for our answer, we have y raised to 4 minus x squared y plus x plus c. So when you are doing this implicit solution, instead of equating to 0, you can just move this to the other side. Negative c is basically the same as positive c. So again, the final solution is going to have something equals c. So to summarize, or rather to shed light on the final answer, it should be equal to equal c. so that it can show the function clearly. So here we have another example where this is our m and this is our n. So trying the variable separable method and the test for homogeneity, we can't apply those methods here, but we can apply the test for exactness. So finding the partial derivative of this with respect to y, we get 3x squared minus 0 since we don't need this and the y gets cancelled out. For the other one, we have 3x squared coming from here since this is n with respect to x, and then we do not need this to y. So we are left with 3x squared plus 0. M sub y equals n sub x, therefore the DE is exact. In this case, we can use the simpler n here because in the other one, the xy is combined. So now it's time to integrate that m, sorry, it's time to integrate n, and we get, so we get 3, sorry, x cubed doesn't have a y, so it gets its own y, and 2y gets a square, and it also gets divided by 2. So we have x cubed y plus y squared plus h of x. So this one is our variable of integration. So recall that since these are mostly in terms of y, then the constant here, or the h of x, the variable of integration, it has to be not y, so it has to be x. So now let's take the partial derivative of the entire thing. So having a partial derivative on all the terms, you'll notice that this gets cancelled because there's no x. In this one, you only need this one. So you have 2x, let's see, 3x squared y plus 0 plus h prime of x. So after getting that, so let's go back here. You can see that on the left hand side, we still have this. So integrating the function with respect to x partially, that basically gives us only this part, since this is the only part with uh, the x, or at least this is what it represents. So going back, we get 3x times xy minus 2, which simplifies to 3 squared xy minus 6x. So cancel the 3x squared y on both sides, and you are left with h prime of x is equal to negative 6. So now you want to integrate h prime of x and integrate this. So negative 6 times the integral of x, sorry, this is missing something, x dx, and this one also needs a dx here. You are left with, wait, yeah, you are left with h of x is equal to negative 3x. So now substitute hx back into the original function. So this is here. So substitute this here, you get negative 3x squared. Okay, so just checking. This one becomes x squared over 2 times 6. So these cancel out. This becomes negative 3x as shown here. And this one, it just needs a 2. There we go. So this is now the answer for this problem. So now, for this example, I already tried variables separable, homogeneous, and exact, and this one still doesn't work. So now, let's try doing linear differential equations. So step 1, rewrite it into a single linear function. So it's going to have something that looks like dx over dy or dy over dx. So if x is on top, we call it linear in x. And generally, we want um, two functions. So the first function, pyx, is going to have a function in terms of y multiplied to x. And then the other one is going to be a function in terms of y without x. Similarly, the other one is going to be linear in y, with y being on top of the dy dx. So there's going to be a function p in terms of x multiplied to y. So the other one is going to be q in terms of x. So let's see. Let's use an equation that is linear in y. Start by multiplying all terms by dx and then dividing all terms by x. So when we start here, again, we divide all the terms by dx. So this will no longer be in the parentheses. And this will have dx in the denominator, like this. So as you can notice, the x is not yet separate from the dy dx. So divide everything by x. So you have 2y over x minus 8x plus dy over dx. So now, look at the format. We are looking for linear in y, right? So look for something that has a y in it and look for something else that doesn't. So this one has a y in it. So this one is going to be our pxy. And this one, negative 8x, doesn't have y in it. So it's going to be our qx. Rearrange it and you should have these variables. Next, you have to determine the if, or the integrating factor. So to get it, let us use, for linear in y, we're going to use px. So again, you have to use this. So whatever you set up here, that's what you have to use. Take note, it's just px without the y. So when you go um, somewhere, sorry, when you go on with your solution, make sure that you don't include the extra variable, only the function in terms of the variable you need. And then the integral will be the same as what's inside the function. So if it's x, it should be x. If it's y, it should be dy. So now we have Euler's number raised to the power of integral of px dx. So substitute your px here. It's going to be 2 over x. So this can be rewritten as um, integral, uh, sorry, twice the integral of x dx, which leads to twice ln x. So a property of ln is that anything multiplied to it can be rewritten as the exponent of what's inside. So 2 becomes the exponent of x, making it ln x squared. So now if you see e and ln, for example, e is in the base and ln is on top. So you could just cancel them out and get only the exponent and their exponent. So now it's going to be x squared. So next, use the general solution to solve the linear differential equation. So recall that this is our integrating factor. We're going to use it to multiply on both sides. It just changes where we multiply it. So again, it's a factor to be multiplied. So it's going to be present here and in here. So for equations, linear in y, we're going to use this one. So remember, if you're linear in y, then you have to multiply it by y. If you're linear in x, you have to multiply it by x. Next, we have qx and dx here. So qx is going to be the other formula. I mean the other function that didn't have the extra variable. And then you have this one. So this symbol is used to represent the integrating factor. And when you substitute that, you should get x squared y is equal to the integral of 12x times x squared dx plus c. So 12, it can be brought outside, and you're left with x cubed dx plus c. So this one, in this case, there's no need for integration by parts. You just integrate it as it is. So this is going to become um, x raised to 4 over 4 times 12. So this is supposed to be 3 times 4x dx. So when you make it in terms of y, just divide everything by x squared. So this is going to be 3x squared dx plus cx raised to the power of negative 2. So in linear differential equations, usually the final answer format is going to be y equals the expression, unless the instructions state otherwise. So now we've had examples for exact and linear DEs. Let's look at some integration by parts to prepare for answering more exact and linear DEs in the assorted examples later. So there are two ways to do it, either through the formula or through the tabular method. So first up, for the formula, we assign a u and a dv following the setting of the u variable in integration by parts following the acronym logarithm, inverse trigonometric, algebraic, trigonometric, and exponential. So this is the acronym LIATE. And we should select the variables to make the u easy to differentiate and the v easy to integrate. So here, we have x squared as the thing that is easy to differentiate, and then sine 3 dx, sine 3x dx is the one that we integrate. So as you can see, when we do it once, it's still not done yet because here in the integral x cosine 3x, we have to do it again. So it might go repeatedly, that's why it's not done here. So we have an easier way to do that, called the tabular method or the DI method. So this is a shortcut that saves time and allows for repeated integration by parts. Each term in the result comes from the product of diagonals of the table. So as you can see here, the red lines show what you have to multiply. So it's positive u v1 times negative u prime v2 and positive u double prime v3. And lastly, it has to be the last term, well, the terms on the last row multiplied, and those will be under the integral. So remember, each term in the result comes from the product of diagonals of the table, and the sign alternates between positive and negative. Only the last row will have the integral sign if it is not 0. So let's see what it is. So we assign u as x squared and v as sine 3x. So the difference between here and the last one is that the other one was dv, but now we have v only. So from a in Liate and t in Liate, let's put them on the table. So the u, or the x squared, will be what we will differentiate, and the sine 3x will be what we will integrate. So looking at the table, we have x squared becomes 2x, becomes 2, becomes 0. So the first stop case we have, the sign that we have to stop the integration by parts is when one of the terms becomes 0. So look at this. Sine 3x, getting the integral of that gives you negative cosine 3x times 1/3 because of the 3 inside. And then multiplying it again, integrating it again, you get um, positive sine 3x times the negative from earlier times 1/3. So it becomes negative 1/9 sine 3x. And then sine to cosine, it becomes negative again. And then the 1/9 becomes 1/27. So as you can see, some functions like trigonometric functions go on indefinitely when integrated. So you need to consider when to stop. So tracing the diagonals, we have x times negative 1/3 cosine 3x here, 2x times negative 1/9 sine 3x here, and 2 times uh, negative 1/27 cosine 3x here. So take note, there are the signs on the other sides. So the first term will be negative, this one will be positive, and this one will be positive. Now for the last row, there is nothing there since 0 times this is going to become 0. So the integral of 0 is going to become c. So we stop integrating when one of the columns reaches 0. Next, when the product of a row is integrable. Since our goal in the table is to fully integrate all the terms, we can stop integrating by parts when the product of a row becomes integrable by itself. So let's have an example. Usually this appears with the ln and the e's. So from the logarithmic in Liate, we assign L and X first. And then from the A, which is algebraic, we assign X to the fourth as V. So in this column, we have starting with this, and then L and X integrated once becomes, derived once becomes X raised to negative 1. And then this one, X raised to 4, integrated once becomes 1/5 X to the 5th. So if you notice this, when you multiply, x raised to negative 1 and x raised to 5, that will simply be x raised to 4. And then it will be over 5. So when we try to integrate this, it is integrable by itself since it's already relatively simple. You just make it like this: x raised to 4 plus 1 over 25. So with the diagonal and the last row, you have this. So don't remember, you still need that positive c. And the third stop case, if a row repeats regardless of the sign. So trigonometric and exponential terms often repeat or cycle between some values. When a row repeats, we can stop integrating by parts. So for example, here, let u be sine x from Liate, where t comes first, is trigonometric, and then let e raised to the x become v from the e in Liate, which stands for exponential. So our d will start with sine x, and our e and our v will start with e raised to x. So have you noticed when you integrate sine raised to x, it's just going to go over and over again. Sine, cos, sine, cos, sine, cos. With the only difference being the negative sign coming from the cosine. Now for the I column, we have e raised to the x. It's never going to change since it's a special property that e raised to x integrated or differentiated is just itself. So as you can see, we have sine x and sine x here. And then you have e raised to x and e raised to x here. So regardless of the sign, this has repeated, so we stop integrating here. So the first diagonal is going to be ex sine x. Second diagonal is negative ex cosine x. And the last row is going to be the negative integral of ex sine x. Now, usually for the third stop case, you want to include the original. You want to include the original in the equation, so that will be here. And if you notice, this is going to be the same as that one. So transpose it to the other side. So you have twice the integral of ex sine x. And since you're solving for only for this, you divide everything else here by 2. So that gives you integral of ex sine x is equal to 1 half ex sine x minus 1 half ex cosine x plus c. So this is the last one. So let's solve this. Integration by parts. So if we have this, let's separate the variables first. As we can see, we have e raised to y on the other side and x squared here. And then inside this y prime, we have dy over dx. So choose a side where you put it on. So first I rewrote this y prime into dy and dx. And then I swapped the positions of it. I moved x squared to the right side and e raised to y to the left side. Rewriting e raised to y as e raised to negative y in the numerator, we can now take the integral of both sides. So now, this is easy to integrate. We can integrate this one. And now this one has to go in the table for integration. So negative y dy. So y is algebraic and e raised to negative y is logarithmic. Wait, sorry, it's exponential, I mean. So from Liate, y will be first. It will be our D column. And in our I column, we will have e raised to the negative y. So I performed integration by parts here. So it should arrive at the answer negative y e raised to the negative y minus e raised to the negative y plus c. So let's see how we can get there using the table. So let's do the t column first. I think we're going to reach 0. So the differential of y with respect to y is 1 and then 0. So we know that we're going to stop after reaching this column. Next, we have the integral of e raised to negative y. So e raised to negative y is itself. But remember that when you are integrating something, you need to apply the chain rule if applicable. So inside is negative y. So normally when it's e raised to y, it's just 1. But if it's e raised to negative y, then it becomes negative. And then for this one, e raised to negative y, the y here, the negative y here makes the sign positive again. So now we look at the pattern here, negative e raised to negative y times y. So this is correct. Minus e raised to the negative 1. So this is correct. And for the last row, it results to 0. So simply make plus c. So now that we have this in either method, you can now return it to the integral. So this is returned here. So you have this here. And then the right side simplifies to x raised to negative 1 over negative 1, or simply negative 1 over x. So switch sides with this, and you get this final answer. Now, at this part of the video, most of what needs to be covered has already been covered here. So in these assorted examples, thing we'll be focusing on are some more harder examples, or if you need practice identifying which one to use in the test, since sometimes it's not stated what you have to do, let's practice some more. So for this one, we don't know what technique to apply here. So let's try first. So throughout the test, you can always start with variable separable, then homogeneous, then exact, then linear. So for this one, 2xy minus 3x squared dx plus x squared plus y dy. Let's see what we can do. So let's try variable separable. If this becomes negative x squared plus y dy on the same side of the equation, it's still difficult to separate. So it doesn't seem to be variable separable since if you move this to the other side, it's going to be hard to separate. So next we can try for the test for homogeneity. So count the exponents in the variables. So here we have 1 plus 1 in x and y. This is 2. This one, wait, sorry. So this is 2. This one is going to be 2 as well. This is 2. But this one is only 1. So we can't apply the homogeneous solutions for this one. So next is time to try the test for exactness. So you get m with respect to y and n with respect to x. So looking at the terms with y here, the only thing we're interested in is 2xy. So 2x gets treated as a constant and y is the one that gets differentiated. So it's 2x times 1. And then for nx, or n sub x rather, we have this with respect to x. So it's only this term we're interested in. So this is going to be 2x. So as you can see, it's equal now. So we can confirm that this is exact. So proceeding, the first step for the test for exactness is to integrate for fxy. So choose something that is easier to integrate, and personally I choose this one. It's easier than the other side. So we integrate this with respect to dy. Correction here, this shouldn't be the partial derivative sign, it should be the straight d. Anyway, integrating this, it's going to be x squared y plus, since there's already a y here, going to be y squared over 2. So it's going to be here. Plus the variable of integration, h of x. So if you're having a hard time remembering what the variable of integration should be, I'll just remember that whatever you use here, it should be the other one. So if you use y here or nxy here, you need to use hx. Because here on the other side, in the next step, we will use mx. Or rather, sorry, not mx, mxy. So take the partial derivative of the whole, and then this one first becomes mxy. So mxy is going to be this one. So it's going to be 2xy minus 3x squared. And then the right hand side of the equation, it will be the partial derivative of 2x of x squared y. So you don't need the y. You don't need this in its entirety, and you still need this. So x squared becomes 2x, and then you treat the y as a constant. Y squared over 2 becomes 0, and then h of x becomes h prime of x. So now that you are able to substitute mxy, you need to isolate this one. So we have negative 3x squared is equal to h prime of x. So now you have to integrate both sides. So integrate h prime of x to find hx. So hx is equal now to negative 3 times x cubed over 3. So this becomes negative x cubed. So now you have hx. You can now return to a function, to this to this one specifically, since you want the function. Wait, hold on. Okay, my bad. I meant to highlight this one. So a lot of areas. So a lot of wait. So this is an area where a lot of students like me are confused. So just remember, when you are doing your substitutions into your final answer, always look for the function xy, since that's what you started with this. So don't make the mistake of substituting back into mxy, since this is already the partial derivative. You need to take the integral. You need to take the integral of h prime of x and put it in the function itself. So for this one, we have h prime of x is negative um, x cubed. And then you have to simply equate all of this to c. So this is going to be our final answer, since for exact, unless the instructions state otherwise, the best answer is equal to c. So for this example, we have x squared y prime is equal to 4x squared plus 7xy plus 2y squared. So we start with the y prime. We make it into dy and then dx for the other side. And then this will be in parentheses now. So first, looking at it, it's difficult to do variable separable because of this one. So it's not something that can easily be factored. So let's try doing the AC method on it. X squared plus 7xy plus 8y squared. So the factors of this could be um 8 and 1, right? But it's not actually valid, since if you want this to be plus, then both of and this to be plus, it's not really going to work, since this should be negative, right? So we can't use variable separable here, since we can't really factor. And even if we do factor, the x's and y's are still together. So next, we try the test for homogeneity. Let's count. So we have 2 in the exponent, 2 here, 1 plus 1 here, which is also 2, and then another 2 here. So as you can see, the terms are all 2, so it is homogeneous. So now we can rewrite it into the general form. We just move the dx that was on the other side earlier onto the left side of the equation. Now rewriting into the general form, we have this with dy and this for the dx. We assign m to be the easier one, since it's just x squared. So we set up our... Okay. So you could assign x squared as the easier one, but I think for some reason I um chose this one for the solution. Oh, okay. My bad. This is actually a typo. This should be n and this should be m. So I'll be updating the slide soon. This is m because it's with dy, and this is n because it's with dx. So sorry for the mistake, but now that we know nxy is x squared, we proceed with y and dy, since x squared is the easier one. So y is equal to vx. So we replace all of the y's. We're going to replace this one and this one. And then we replace the dy here with vdx plus xdv. Later on, we'll be using v is equal to y over x. It comes from here, dividing both sides by x. So now, substituting, we have x squared vdx plus xdv plus all of this dx equals 0. So personally, I like distributing the negative sign here because there tends to be a rearrangement of terms sometimes. So for example, here in this vdx plus xdv, there's going to be um, x cubed for the dv. So as you noticed, remove I didn't remove it from the parentheses anymore. I just regrouped them. The x cubed dv goes here, and then the other one with the vx is going to be vx squared dx. So since the dx is still outside here, when I put the vx squared in here, I just put it as vx squared. So no need to remove the parentheses and make your no need to make it longer, the computation. Yeah. So now inside this parentheses, we add like terms. So vx squared is going to go here into 7. So it's going to be 6. So negative 6 vx squared. Next, we can factor out the 2 here. You can also factor out the negative sign. So this one needs a negative 2, and then negative here also. So now you move the x's and the v's onto different sides. So you have dv over v squared plus 3v plus 2 is equal to 2x squared dx over x cubed. So we call the negative sign. So now on the left hand side, it's difficult to integrate. So we're going to do partial fraction decomposition. So you do partial fraction decomposition if u substitution doesn't work. So for example, try u substitution first. The denominator there will become 2v plus 3. But you don't really have anywhere where you can use this 2v plus 3. So you can't put it in the numerator. It's not even there. So if you can't use u substitution, proceed to partial fraction decomposition. So v squared plus 3v plus 2 factors into v plus 2 and v plus 1. So set those as the denominator. And then write a and b to represent their numerators. Cross multiply. So you have a times v plus 1 plus b times v plus 2 is equal to the numerator on the other side, 1. By the way, even if the numerator here is dv, do not write dv in the partial fraction decomposition. You only want the numbers. So if it's 1 dv, you have to use 1. So next, you find values that will make these 0. So this is going to be negative 1. So that a will become 0. It's eliminated. And we're left with 2 minus 1. It's 1b. So 1b is equal to 1, and this part becomes 1. On the other hand, we have v is negative 2. So negative 2 and the negative 2 here will give us negative 1a. And the 0b will be eliminated. So we get negative 1 is equal to a. So this one is going to be negative 1. So recall earlier, I dropped the negative sign. So we can expect that when we apply this, we have to keep the negative sign again. So here, this one is now this, and this one is this. So I skip directly to integration, and again, the negative sign must be here. So all of this simplifies to ln since this is a linear function with no coefficient. So it's just ln v plus 2. You can skip the u substitution if you want. So this is negative 2 ln x. This becomes positive ln x. And then the 2 gets moved to the exponent. So it's x squared. So correction for this one, it shouldn't be in the denominator. It should be x squared times v plus 2 plus 1 is equal to c. It's not the final answer. I forgot to mention that we still have the v. So the v here, we call that y is equal to vx. So dividing both sides by x, v is equal to y over x. So you have to substitute it back. And then this is going to be one of the acceptable final answers. So again, the x squared must be in the numerator. Okay, next for the assorted examples, we have this one. So let's see if it's variable separable. Doesn't seem to be. Okay, so at first glance, it may seem like variable separable, but this is actually x minus 3ux. And if you move the 3 here into the left side inside the du, it's just going to be like this. So it's let's see. Okay, so it doesn't seem like it's variable separable. So next, let's check if it's homogeneous. We have u. This is 1. This is 0. This is 1. Oh, wait. Sorry. Rather, we have to distribute the x first. So it's going to be x minus 3ux or 3xu. So the exponents of this will be 1, 1, 2, and then 1 for the 3u. So it's not homogeneous. So what can we do now? Let's start exact. So we rewrite this as ux. Okay, so now that we're here, um, try to get, okay, so this one is our m. So since the other variable is not y, we have to use u. So m with respect to u, and then n with respect to x. So m with respect to u is going to be just 1, and then n with respect to x is going to be 1 minus 3u. Yeah, just 1 minus 3u. So as you can see, it's not the same. So it's not exact either. So let's test now if it's linear. So first we check if it's linear in x or in u. So according to my calculations, it seems to be linear in x. So what we have to do here is, again, we have to move this to the other side. So we have 3u du minus 1 minus 3u parentheses x du. So we simplify this, and then we divide both sides by u. So the 3u du becomes just 3u, and this one just becomes negative parentheses 1 minus 3ux. So if you noticed, I didn't remove the x here since the formula says that we need linear in x plus a function of u times x equals a function of u. So from the given, I can see that the x is already multiplied. So I tried the x linear in x first. So now with dx over du, there's still a u attached to it. So divide everything by u. So this is going to be 3 only minus 1/3 u over u. So rearranging it into our formula, we can identify that um, function p in terms of u times x is going to be this one, and the function of um, q in terms of u is going to be 3. So next we have to determine the integrating factor. So the integrating factor comes from pu. So if you notice, it's pu only, not including the x. So this is what we will substitute in here. So with Euler's number raised to the power of the integral of pu du, we have this. We can rewrite e as exp, so it's easier to write on our test paper. We can bring down the exponent, so we have more space to write. Next, for this one, you separate it first into 1 over u minus 3u, which becomes 1 over u minus 3. And then you can distribute the integral sign and the du. So it's going to be like this here. Next, the integral of this is going to be ln u, and the integral of this is going to be just u. So ln u minus 3u. Next, you can separate this into two Euler's numbers. So you can get e raised to ln u times e raised to negative 3u, or if you prefer, e ln u over e raised to 3u. So I prefer this one since it keeps things neat and it keeps things linear. So after simplifying, you can cancel the e and ln and be left with just u, and then you're left with e raised to negative 3u. So this is our integrating factor. So next, the integrating factor is going to be here. So remember, we are linear in x. That's why we multiply the integrating factor to x. And then the other side is going to use qu integrating factor du inside the integral. So remember, if we already used this one earlier, it's time to use this one. So this is just going to be this one times 3. So we have 3e raised to negative 3u times u du. So this one, we take out the 3, and then we integrate by parts. So from here, we have exponential and algebraic. So by Liate, this will be our d, and then our I will be e raised to negative 3u. So perform the integration by parts. First we do the differential, so we know if it will reach 0. And then we do the integrals. So again, when you do the integrals, don't forget the chain rule inside. So when you do the chain rule inside, it's going to be this one. You keep this times the derivative of negative 3u, which is negative 3. And then you do that again. This one is kept. And then times negative 3 again. Times negative 3. It's going to become positive 9 e raised to the negative 3u. So now here you get the diagonals. So that's negative 3e raised to negative 3u times u. And then negative 9e minus 3u. Negative 9e raised to the negative 3u plus plus the integral of 0. So that's going to be plus c. So now you can substitute it back into the equation. So this is where it was at earlier, and now it is this one. So distribute the 3. Oh, wait, rather, sorry. You don't distribute the 3. I meant you factor out the e raised to negative 3u. Since it is common on both sides, we can now eliminate it. So it's not here anymore, and it's also not here anymore. We're left with this one. So now you can distribute the 3, and you're left with x is equal to negative 9u minus 27 plus c. So keep your final answer like this, since for linear, we want x um, to be, it's equal to x, since um, this is, what is it called again? The independent variable. Wait, no. This is the dependent variable, and we want to keep our answers this way unless stated otherwise. So this is going to be our final answer for this number. Now, for the next number, I'm not going to go over this in detail, but I'll just show you the steps, since there won't be a problem this hard in our exams, hopefully. So if you ever see something like this with a square root, you can test for homogeneity because most likely it will be homogeneous. So if you have to do a lambda test, this is what I mentioned earlier. If you have to do a lambda test, um, a lot of students would just count the variables inside the square root by mistake. So they're gonna think it's 1, 2, 2, 1, but not really. Since there's a square root here, it's actually going to be square root of 2. But you can't just pull it out of the square root. That's mathematically incorrect. So you can't do the visual inspection here. But what you can do is um, use the lambda test. So the lambda test for homogeneity means that you will just add a lambda before each x and each y. So y becomes lambda y, x squared becomes lambda squared x squared, and y squared becomes lambda squared y squared. So these lambdas, you can factor them out. So this is the original thing in the integral. You factor out h squared, it's just going to be h after passing it through the square root. And then, sorry, it's not h, it's lambda. After passing it through the square root. And then there's a lambda here and a lambda here. You can move it out again. So you can see that the lambda is outside of the function now. If this is your original function, so if this is your original function and you factored the lambda out of it, so this needs a parenthesis. If you factor the lambda out of it, then this is already homogeneous to one degree, I think. Please double check if it's degree or order. I forgot. So if you did this, then it is homogeneous now. Now for the next steps, I'm going to skip over them. V substitution as usual, and then here, trigonometric substitution. So we won't encounter something like this in our exams, but trigonometric substitution allows you to substitute tricky values like this one if we do not have any formulas for it. So if we don't have any arc signs, if we don't have any inverse signs, then we proceed to trigonometric substitution. So basically, you're going to um, assign a variable as a number times a trigonometric function. And then from that trigonometric function, if we use tangent, you're going to assign an opposite and an adjacent. And then we solve for a hypotenuse or vice versa. So it's a very long process, but initially, what it lets us do is to um, clean this up. It makes us let it turn into a number. So when you reach this point, you also have to this first you have to solve for c as always, and then after solving for c, you have to substitute it back. So I think that's all for this video. So good luck for the upcoming exams, and I hope that I hope that these solvings have helped. So especially since there are a lot of errors, like this, it has to be, for example, this one has to be negative and such. I hope that seeing the process in real time, how you're going to go over your solution, helps with identifying the common mistakes at least. So thank you for watching and good luck with your exams.